We know that starting from this March, Apple has introduced Face ID with mask. There are so many positive reviews regarding this Face ID, and most of them say that it is very reliable in terms of privacy and security. But have you ever considered why did the previous version of Face ID cannot recognize your face while you are wearing mask? This could be vexing for some users, especially during this COVID-19 pandemic as we need to wear masks every time. My name is Surya, and I would like to share my final year project towards interpretable and robust face recognition by introducing neural network model that is able to recognize occluded face via facial mask. Throughout this presentation, we will go through several things. First, we will understand how face recognition identifies our face with and without mask. And then we will also see the models used in this project. And last but not least, we will compare the performance with existing results and give suggestions for future improvements. So, how does face recognition system identify our faces? Due to the black box nature of neural network, there is a lack of visual evidence that make these models hard to interpret during decision-making process. And as such, a number of research regarding this has been conducted. In the area of face recognition, interpretability could be measured by seeing which parts of the face used to make prediction. And as we can see in right figure, face recognition system tends to learn more structured face representations, such as eyes, nose, and mouth. And this raises a question whether the system will behave differently if we use facial masks to recognize our face. In face recognition with masks, occluders are generally contaminating the nearby features, including nose and mouth, and consequently degrade the overall performance of the system. And to tackle this problem, existing neural network models need to be adjusted by focusing on the eyes region of the face for predictions. And in the next section, I would like to explain the model architectures used in this project. So we train 4 different models for this experiment. The first model is variant of ResNet 50 model, which is called LResNet 50 EIR. This model is one of the most popular benchmark for face verification evaluation. The next model is TDMPNet with VGG16 backbone. This model is known for its robustness against partial image occlusions by filtering out occluded features in a recursive manner. Next, we will also have TDMPNet model, but with LResNet 50 EIR backbone. And lastly, we have object detection model called DTR that consists of LResNet 50 EIR as the backbone and transformer encoder decoders. We also tried several combinations of DTR model, such as using only transformer decoders, local fully connected layer, and extracting feature maps from last stage of the backbone. And all models are trained using Cassia web face dataset that contains 10,575 identities with the total of more than 450,000 face images. As for the evaluation, we use LFW and self-generated mass LFW dataset, which each of them contains about 6,000 image pairs. Now, we will look at the results of LFW dataset. As we can see in the table, the combination of the TR model that uses only transformer decoder and global fully connected layer performs the best with the accuracy of 99.23%. We also observed that using VGG16 as the backbone will degrade the performance. One of the main reasons is because VGG16 network is generally less complex compared to the ResNet 50 variants. Now, we will look at the max LFW evaluation results. From the table, we can see that the same DTR combination obtained the best accuracy. And in the next slide, I would like to show the visualization on why this model performs better than the others. From the visualization, we discovered that the DTR model could surpass all other baselines because it is able to produce similar attention weights regardless of facial mask assistance. In addition, from the bottom right image, we observed that every attention weight could focus on different parts of the face, which makes the predictions more reliable compared to the single attention weight. After we look at the result, we observe several factors that could limit the model performance. First, we notice that there is a lack of evaluation benchmarks, especially for the facial mask face dataset. And in general, we need to have more than one evaluation benchmark on such dataset, and for the future implementations, we suggest adding the AR face database as another evaluation benchmark. And in order to prevent overfitting, we also recommend to train the models on the larger dataset, such as Microsoft Celeb 1 million. In terms of the robustness against image occlusions, we analyzed that the DTR model may not perform well if we block out the eyes part of the face, and one example to do this is to use sunglasses. As for the improvement, we suggest experimenting more on the backbone selection, especially on transformer vision-based models, such as VIT and Swim Transformer. So these are the resources used for this presentation, and thank you for your attention to this presentation.